background is also a little bit of interdisciplinary, so I think it really fits with the aim of the center here. So today, let me talk about the Skyrmions from different perspectives. So this is what I've been working during my whole career. So I started in Spain, working in Skyrmions more related to high energy physics and nuclei. And then I also moved to study this kind of structure, solitons and defects in condensed matter systems. So this talk will be also kind of a tour of my career, just taking you from different aspects where these Skyrmions can occur, where they have some role, and where I was able to study. So these Skyrmions are topological solitons. So let me just give a brief introduction of what does it mean. So first of all, the first soliton was discovered by this guy here, John Scott Russell, in the Edinburgh Canal in the 19th century. So he was just riding his horse along the canal, and there was a boat there, pulled also by a pair of horses. And this boat just suddenly stopped, and he saw like a kind of wave emerging from the front of the boat. So he was quite intrigued by that object, and he just went after it, riding his horse, until I think he just got tired, went back home. But then there in UK you have all these rear gardens. So he just went to his rear garden, and with a time tried to also to have experiments and to recreate these kind of objects. So then he saw that there were like really, really stable objects. He also saw when just pursuing this object, the solitary wave, as he called it. So he also managed to just get both of them interacting, colliding, and he saw that they emerged and changed. So the stability was really a thing there. And they just conserve the shape and propagate with constant velocity. And here you can see like a recreation of this wave in a conference in 1995. So you can see they skip the horses, but you see that they just had the boat, stop it, and this solitary wave emerged. So as I said, they are really stable objects. So now we also took somehow this term for the configuration that we're interested in, which is these topological solitons. So they're characterized because they are really they are very stable objects. But in this case, the stability comes from the topology that we have in both the target space and the base space. So our space of coordinates, the physical space, and also the space where the fields live. Usually they appear as collective excitations of some degree of freedom and as solutions to nonlinear equations. And since we have topology in the system, so we have a topological number or chart that we can identify, and because of this topological nature is conserved. And somehow we can think about this topological charge like a number of particles. So this brings us to, to my friend here, which is Tony Skyrme, who proposed the Skyrmion. So he proposed an effective field theory for QCD, for quantum chromodynamics, where the nuclei appear as collective excitations of the fundamental units of freedom. And remember that I just mentioned that in these theories, we have some topological chart, which is conserved. So he identified this topological chart with the baryon number, and then it's a natural way to ensure that this baryon number is conserved. So this is how the model looks like. So we have the Lagrangian here, and it's very simple. So we have our field. So the fundamental degree of freedom is an SU2 field, this U here, where we can just construct these currents, which are SU2 algebra valued currents, and they enter just in the Lagrangian in two terms. We have one term here, which is just mu, so it has two derivatives. And then we have a term which has four derivatives. So you can see that I remember that in this theory, the fundamental degree of freedom that we have are pions. So we have pions encoded in this U field here. And you can see that these terms give you exactly just the kinetic term, so a standard kinetic term for this pionic field, while this quartic term so it doesn't have any meaning in that sense. If you go to this expansion in these pions and go to this just to quadratic order, you see that there is no contribution here. This is higher order contributions. So why do we need this term here? Well, we will see later, but it's because of the stability. So if we want to have the solitons and to be stable, we need this quartic term, and that's why basically he introduced it. And also, I've just written here, but it's massless, because if we at the end want to encode pions here, you will need a term with the pionic mass. So people usually also add just a potential, giving this mass to the pions. And then this U field has to take a finite value at infinity, so our energy is bounded. And that allows us, usually we just take to the identity, which indeed comes from this mass term. And in that case, you can compactify your basis space, or the space of coordinates, which are 3. You can identify all the points at infinity with 1 point and compactify this R3 to a 3-sphere. SU2 is also diffeomorphic to a 3-sphere, so this U field is just a map between 2 3 spheres. And it was a topology starts to appear. So we can define the topological chart, which is the 1D number, so the number of times that, if we go once around the 3-sphere in our space of coordinates, so we just cover these coordinates, all the points once, then we go to the field and we see that it can also cover the target space a beta number of times. And that's how we define this topological charge B, which will give us the baryon number. And then we also have, which it will play a role later, a BPS energy band. So BPS stands for Guamoni, Prasad, and Sommerfeld. And it basically means that we have a lower band for the energy, and this band is topological. So we don't need to have a solution to find this bound. And you see that this bound is linear with the baryon number. However, in the case of the standard scale model, we cannot reach the bound. So we are always over the bound, but there might be models where we can attain this bound, and it will be important later because it will have some properties that we will be interested in. So let me just go back to why this fourth term here, and that's what is called this Derrick theorem. So we need it, as I say, for the stability of our configurations. So to see that, we can just consider a scale transformation. So we just take our coordinate x, and we send it to lambda x. And if we take this transformation to the energy, we see that the E2 is the first term, so the one with 2 derivatives. The E4 is the term with 4 derivatives. And we see that they transform in this way here. So we have lambda power to -1 and lambda. And you can see, this is a scale transformation, you can think like, okay, if I don't have this term here, I only have this term, I could minimize my energy just sending this lambda to infinity, right? But then we send you the energy to 0. So then, like these terms, what they do is they try to shrink or to expand your configuration. So you want to have a balance between these two so that your configuration has a finite size, and it's stable. So for that, the theorem tells us that if you calculate the derivative with respect to this scale transformation and evaluate at lambda equal 1, it has to be 0. So basically, it's telling you that lambda equal 1, so no change of the size, is a critical point of your energy. So you want to have these Soliton configurations, you want to have the Derrick theorem in place. It doesn't tell you that solutions exist. You can have this, and then perhaps you don't have these solitons. But at least if you want to have solitons which are stable, this is a must. So that's why we need the Quartic term in our theory. And this is just how the configurations look like. So here we're just plotting the energy density, the baryon density, so isosurfaces of the baryon density that I showed you before, so this charge density, and we just find what the Skyrme model gives us, like for baryon number up to 8. So it will be like nucleon, so neutron or proton, and nuclei up to baryon number 8. So let's just deepen a little bit more in this Skyrme model, right? Because I mentioned, so people have studied this, basically trying to describe nuclei or nuclear matter. And so everything started in the 60s of last century. Then also people like Witten, Atkins, and Napi had studied this model, but then it was like forgotten a little bit, or more than a little bit. But in the last decades, especially with people from UK, so the field had a revival. So people started to got interested again in this model, and they did a lot of things, sounds very successful, like for instance, the spectra of light nuclei. So they could quantize the model, and for instance, for the alpha particle, so the helium equal 4, they managed to describe the excitation spectra. And for instance, they managed also to describe the carbon-12. It's known that the carbon-12 have the ground state, and there is also an excitation state, which is called the Hoyle state. And they managed also to describe these bands of excitation of both configurations quite well. But on the other hand, we still have some issues. And for instance, like this Skyrme model, the minimizer for large B is a crystal. And this is a problem, especially if one want to describe neutron stars, because it's known that inside a nucleon star in the core, what you have is more like a fluid. So describing a neutron star with a crystal is a little bit of dots. So there were some issues there. So people have tried to implement, alternatives to that and trying to improve. And then there are some difficulties, or I would say even problems. And one is like large binding energies. So if you take this description for nuclei and calculate the binding energies, in nature, the binding energies are around 1%. But however, this Skyrme model gives you energies of about 10%. So it's 1 order of magnitude higher. And also, it's known that, for small nuclei, you have also these alpha clusters. As you saw before, what this model gives you, the configurations are more like shell-like structures. So, there are like some problems when you want to describe like proper nuclei, that's the one you find in nature. So focusing especially on these binding energy problems, people have, proposed some extensions or modifications of the model. And here we have, again, what I mentioned before, this BPS model. Remember, this BPS model just means that we have a topological lower bound for the energy. So our energy cannot be lower than that. But this bound depends, so it's linear with the baryon density. And that's important because if we can saturate the bound, then the binding energies are just zero, right? Because if EB is just the energy of a nuclei, of a soliton Skyrmion with baryon number B, we just have zero, right? B times E1, but here we also linear with B, so it's just zero. It's not what we want either, but it's a good starting point. So we can introduce more contributions, or perhaps we can be close, but not exactly at this BPS bound, then we can manage to describe these lower binding energies. So with that in mind, there are two proposals. One is what is called this BPS Skyrme model. And in this theory, so remember that at the end, this Skyrme model is just an effective field theory. So we could add more terms, perhaps. We could think about which more terms we can add. And that's what they did here. So they just consider a term which is with six derivatives. So we have the 2, 4 potential, and they added a 6th derivative term, which is just the square of this baryon topological current. But then all the proposal by Paul Sutcliffe is just to couple the model to vector mesons. And this is the one I will focus now. So this is, we will skip this part today. But so we can see what we get with this model here. So for that, our starting point, if some of you are familiar with holographic QCD and the Sakai-Sugimoto model, so this is basically equivalent to that, but in flat space. So what does it mean? So we start with a jamming theory in one higher dimension. So instead, in our physical 3 dimensions, we go to one higher. So this is the energy functional. And it also has a BPS bound, right? Which is this one here. As you see, again, linear with the baryon number. So we can just work a little bit with this. And since here, we have this gauge potential A, so we can just fix the gauge, which is like in Z is this 4th coordinate, right? So we have X, Y, Z originally, but now this X, Y, Z will be X1, X2, X3, and Z is just this additional coordinate. So if it's the gauge that component is 0, we can expand the other components in terms of what is called these Hermite functions, which are related, they're not exactly the same, but they are related to the Hermite polynomials. And doing that, we see that this gauge potential just has some term where, again, we have some U, which are SU2 matrices. So this reminds us a little bit to what we saw before, right? With this right currents. And then an infinite tower of vector mesons. So these V here are vector mesons. So now it's clear that, when you have the infinite tower, then you are exactly in this bound. So it's linear. But you could, of course, you cannot add an infinite number of vector mesons. So you can think, okay, what's happening if I just add 1? Would it help reducing the binding energy? So that's what we wondered, and that's what we did. So they just consider the first in the queue, which is the rho meson. This is the lightest of these vector mesons. And then, so we have just like 3 contributions. One is the same as we had in the introduction, that is a Skyrme energy density, so the quadratic term plus a quartic term, and then we get some ugly and complicated expressions with just, the meson, so the raw meson contribution, the kinetic term plus the mass and some vertices of interaction, and then the interaction between the Skyrme field and the raw mesons. And as you can see, there are a lot of constants here. But one good point is that, in this Skyrme model, we only have two free parameters, which are the energy and the length scales. And even if you see here, all these C constants, so if we go back here, all of them come from integrated over this set coordinate, this additional coordinate. So even we have a lot of terms, we still have only two free parameters, this energy and length scales. And so we can see what's happening with the energy. So here we just plotted the energy in terms of this BPS bound, and we see the red squares are those coming from the usual Skyrme model. So you see that there are almost 25% over the bound. But once we add only one vector mesons, we manage to lower the energy quite a lot. So we go from this 25 to a 6%. But we still have a problem, right? Because we want to describe like physical objects. Remember that all this is without massive pions. So we don't have the potential anywhere. But that's not a problem because we know how to do it. And we can include it by hand. So it's what we do here. So this potential, which are the trace of the identity minus this U matrix, just give us the mass. And people have already studied that in the standard model. And what they saw is that it has an effect. Because including the mass, I mean, if you remember, we have like these kind of shell-like structures. But once you include the mass, these structures start to get flattened. So for instance, for mass equal 1, it's slightly bit flatter in this direction. So it's like the top view of this. And then if we go to mass equal 2, then the configuration is quite different. And it's like really like a smashed Skyrmion. But we have also a problem. So here we are talking about m equal 1, m equal 2. So this m is just the one here. So this is just the correction for these factors. And the physical values, if we take the values that are usually used in the Skyrme model and plug just the pion mass, so you see this m is around 1/2. But here, to see the effects, we are going to really high and unphysical pion masses. But okay, we can also add this here. We will take this value, the physical one, and see what's happened. First of all, we go to the energies. Again, so now here these are the mass per nucleon, so give us an idea of the percentage of the binding energy. And you see the blue squares are the values from the experiment. As I mentioned before, around 1%. The red dots are from the model, from the standard version of the model without the raw mesons. But once we add these raw mesons, you see, we managed to go quite close to the experimental values. So we go from this 10% up to about a stack of these block type skyrmions, but this in liquid crystals. And there are also, I mean, liquid crystals is a system where you can find a lot of different of these configurations. And also Professor Ivan has found another kind of solitons, which are these elignotons, which are related to what are called Hophions. So Hophions, remember that in the case of the Skyrme model, if we look at our space of fields, it was a 3-sphere. So in the case of solitons, our space of fields is an SU2 sphere. But you can also define like a topological chart, which is called like the Hopf index, and you can indeed plot this kind of charts. And in this case, what you use, you take your, so usually, as we will see in these liquid crystals, our fundamental degrees of freedom, so order parameter is a unit vector. So we can plot 3 pre-images of this unit vector, and we will have like 2 curves linking together. So the number of links that we have is the number of this Hopf index in this case. So let's just give me, to be a little bit more into detail for these liquid crystals. Also here you have experts which know much more than me. But so as I said, in this case, our order parameter is just this n vector director, which just give us the orientation of the molecules of the liquid crystals. But these molecules are characteristic because they have like head to tail symmetry. So there is no like a preferred direction. So we cannot distinguish which is like up or bottom, like, or if in a row, if we have like a head or not. So then our field is not a map, from R3 to R3, but to the projective space, because what we have to do is to identify the vector n with the vector minus n, right? So you cannot distinguish in this case if it's just pointing up or down. I mean, it's the same, because you have like this rod-like structure. And here we have like 2 phases that can appear in liquid crystals. So one is the zematic phase on the left. So basically it's an uniaxial phase. So you see that there is only one direction. So basically this end vector just points, well, not points, indicates the direction where these molecules tend to orient it. So it's like the average we call theta 0. Okay, something like in between the other two phases. But there is a problem, and is that the Franco-Sim free energy is not able to just characterize this kind of systems. So having that in mind and how to describe these systems in the case of achiral molecules, so when you don't have a preferred direction, Professor Epifanio Virga just proposed some years ago a generalized elasticity theory. And indeed, this is somehow as we had in this Skyrme model, because now, so this first line is just the Franco-Sim free energy. Well, remember, we have everything which was quadratic in first derivatives. So he proposed an additional contribution, which is fourth order. So it has fourth order in first derivatives. So it's basically a combination, of these quantities, but the square, which is also something like what we saw before, right? For the Skyrme model. Do you remember we had like this quadratic term related to this kinetic energy, but then Skyrme came and added the quartic. So the stable solutions could exist. So here we have something similar. So we have the quadratic plus this also quartic contribution. And one thing that you need to be able to describe these three bendematics is that this K3 has to be negative. So once you have that, you can just see that this configuration for the n vector just describe what I showed before. So this twist band phase. And then you can just see that you can plug this expression back to your free energy. You can minimize it and also get analytical expression for the theta 0. So this angle, with the symmetry axis, and also for the beta, which is basically related to the pitch. It's 2 pi over the pitch. And you can find those values just in terms of these elastic constants. So then, okay, so we arrived in this with my collaborators in Italy when I was a postdoc, and I started to work a little bit in these liquid crystals, and we thought, okay, so, well, we know, this have like this n vector. We know some theories, which called this Skyrme-Faddeev theory from high energy physics, where you have something similar. You also have quartic contribution. So can we perhaps look at some solutions there? Can we also look for localized solutions, as we know that, like this kind of solitons and defects? So that's what we tried. And indeed, we tried to describe what we call the Skyrmion tubes, which indeed Professor Ivan and Andre have also found experimentally in chiral liquid crystals. So we also tried to see if this theory can host these objects. And the answer is yes. So we proposed just an axially symmetric ansatz. So basically, we added a winding around the azimuthal angle. And then we allow this f, which we call perfect function, is basically this angle which shows you the deviation from the from the axis of symmetry, right? So you know that at infinity, so when you just go to the background, it has to match this theta 0 of the twist bend phase. But then we allow it, well, we ask for this value to be 0 or pi at the center. So in this sense, we can have these localized solutions coming just from, that these vertical molecules just tilting until this theta 0. And we also added a magnetic field. And I think this is interesting because, so I mean, here we have 0 or pi that, remember, in this liquid crystal, you had identification of going from n to minus n. So it might look that there is no difference here, but there is, because basically it's telling you, like if you go to theta 0, you have like two ways of going through it, right? You can rotate in one direction or the other one, basically. So it's telling you, you just take the short path to theta 0 or the long path to theta 0 through pi. And that's important because so if now we add this coupling to an external field, there will be a critical field, right? Well, we have a phase transition from this twist band to the nematic. So what's happening is that these molecules will tend to align with the external field. So once they are aligned, basically all these will point up. So we just recover the nematic phase. So we can study that. And indeed, so these are just this profile. So how this angle with the axis change. So we start like at 0, and we see that so the red is without magnetic field, and if we start to increase the magnetic field, sorry, we end up just at the nematic phase. Right? So we had just all these molecules are vertical everywhere. It's something that you would expect. But if you start at pi, what's going to happen is, yes, again, so the magnetic field is taking us our theta 0 to 0. but we are taking the long way. So basically, we will still have the pi. So we are just twisting. Oops, sorry. So we are just twisting the molecules going from pi to 0, and we still have this profile here. And then is what this Skyrme tube is, right? So this is like a representation. We are like with cylinders representing these molecules, and you see, so this red is pi, so it means that it's vertical. But then it goes change from pi, just twisting, it's just horizontal and back again to vertical. But then we still have this core, so we still have these Skyrmion tubes. So that's another example of where Skyrmions can play a role, like in liquid crystals. But there is even more, and also Professor Andre has working, for instance, in frustrating magnets. And he found that there you can have, for instance, this picture here is just a crystal of Skyrmions. Right? So you also can have these kind of structures. But well, I mean, I came also from this field, right? When I started to study these nuclei from this high energy physics, and all these configurations are quite different from the one that I started to work with. So we asked, would it be possible also to have these kind of structures in condensed matter system? And the answer is yes. And indeed, this frustrating magnets is the place to look for it. So first of all, let me just review a little bit. I'm not an expert either, but what this frustration means. And for that, we can think that we have just an antiferromagnetic interaction. So we have a chain of spins, for instance, in one dimension. And this antiferromagnetic interaction is telling us that if the first spin points up, then the second has to point down, and the third point up, and so on. And we can go also to higher dimensions, like, okay, let's think about a square lattice. So we have the same thing here. So we start with the top left corner, it has to point up, then on the right has to point down. And if we go just to this corner here, okay, we know that the closest is this blue one, so it has also to point down. Oh, sorry. It has to point down, and then you just need to complete with the last corner, which it has to point up again, right? And now everything is fine because the nearest spin is just pointing in the opposite direction. But what's happening if we, for instance, consider a triangular lattice? Well, here things are more complicated because, okay, we start with up, we go to the top vertex and it's down. But what's happening in the third one? It doesn't know what to do, right? Because we have already the closest neighbors, it has already the two possibilities. So how the system, works it out, it just they basically takes the spins out of the plane. And we have examples also of these frustrating materials in 3 dimensions. Probably one of the most well-known is this pyrochlore lattice, where in this case, what we have are 4 spins in a tetrahedral cell. What they decided is, okay, how this they overcome this frustration, right, that they feel. So, well, they decided to just pointing an all-in, all-out configuration. So this bluish tetrahedra are all the spins pointing out, while in this yellowish are all the spins pointing in. So at the end, this frustration means that our ground state is non-collinear, right? So we have some spins which are non-collinear, and that will be the key point to try to find these 3D Skyrmions, similar to the one that we saw also in the first part of the talk. So to see how this is possible, let's just consider that we have 3 spins per side, and they are orthonormal to each other. So we can just encode these 3 spins in this way, right? So this R is just telling us each kind of a spin that we have, and then this capital R is just an SO3 matrix. And we write it in terms of a basis, which in this case, since they are orthogonal, they are just the Kronecker delta. But alternatively, we also have, we know that we can write also the similar thing in terms of SO2 matrices. And for some strange reasons, we decided to call it also U. So an SO2 matrix, which is called U. So it might start to look familiar. And so we can also see how, if we take 2 spins, for instance, like next to each other, like these nearest neighbors, and consider the spin-spin interaction, how does it look? So, well, if we go to the continuum limit, which is basically a Taylor expansion, we see that this is translated in a term which is second order in derivatives. And indeed, if we just consider this representation here, we see that we can just stress derivative u, which is exactly the same thing that you obtain in the Skyrme model. So if you remember that you have this trace of currents mu, if you write those currents in terms of u, you get exactly this. And so we can also write it in terms of some currents, which we call here J, that is slightly different, but basically the J are the only difference with the ones we had before is a minus sign, so it doesn't affect anything because they appear square in pairs. So we see that this spin-is interaction give us exactly the same quadratic term that in the Skyrme model, which is called this principal carrier model. So it looks like a good candidate to find these objects. But of course, remember that a quadratic term alone is not enough. We need, for instance, a quartic term, further contributions to stabilize this soliton. But okay, it's looking promising. And we can even go to a more general case, where is when these spins are not orthogonal to each other, but they form an angle between them. So which is the dot product is given by this kappa, is parameterized here. And we do the same, what we see is that we have here, again, the same. So these three currents. So A here, basically, you see, is the spatial index. So just come from the derivatives. And this R is just the index in the inner space of the fields. So we see that we get the same current square, but is corrected with this beta factor, but only affecting the third component of each current. So basically what we have here, instead of have the target space like a three sphere, is a squashed three sphere. So we are squashing this third direction with this beta factor here. So now we know what we need where to look at, so we can just to build a toy model. So we will consider a qubit lattice with a spacing A. And now we go to the more general case, which is where these are not orthogonal to each other. Well, indeed, it's more general, so it can be, it depends on kappa, right? So when kappa is equal to 0, they are orthogonal to each other. So we are exactly in this Skyrme model framework. But if kappa is different from 0, then we are in this squished sphere. And indeed, somehow this, if we go to the string case also where kappa is equal 1, what is happening is that all our spins are the same, right? So they are collinear. And then our target space is not anymore S3, but S2, which is the place where these hopions, and I showed before in liquid crystal, live. So somehow it's even more general, and these kind of materials can give you, like this interpolation between these Skyrmions, but also arriving at these hopions. So for that, they just consider now this general case. So our basis is more general. So we write in terms of this angle theta. So kappa and theta are related. And we just consider a Heisenberg model. So we consider that we have a spin-spin interaction, which at nearest neighbors is ferromagnetic. So this kappa, K1 has to be negative. But we consider that at neighbors at a distance 2a is antiferromagnetic. So this K2 is positive. And we also, we are also considering like interaction between the same species, so R and R, which are the same spin. So if we go again to the continuum model to see, because remember, we needed this quartic term, so we can go again to the continuum model and now expand until the fourth order. So that's what we get. And we have, as we were expecting, right, this quadratic term we saw before and a quartic term here. And this is exactly as the Skyrme model. Of course, now this quartic term, if you write it instead of these J currents, will be different. It's not the same contribution that we have in the Skyrme model, but that's not important. I mean, remember that we wanted that term just to be able to have these stable solutions. So this will make them work perfectly, but then we need to recall this direct theorem. So remember that there has to exist a balance between these two terms. And for that, in the case of the Skyrme model, I mean, you arrive at that balance because the energies were positive definite. They were just something square, which is also the case here. But so we only need to worry about these coefficients being positive. So if these coefficients are positive definite, then we can have these stable solutions. And that just imposed these constraints for the parameters that we have for this coupling, the ferromagnetic and antiferromagnetic couplings. And we will be looking our solutions around the Lifshitz transition, which is where this coefficient, the point where this coefficient goes from positive to negative, because then we ensure that our solitons are large enough so this continuum approximation can work. So now we have a theory, and we can just try to find these solitons. But for that, I mean, now that we know it's a good place to look at them, we will go back to our to our lattice model, and we can just solve the lattice model itself. So remember that we only have these spin-spin interactions, but we could work perhaps with the spin directly, but that's quite complicated because you see, I mean, remember that these spins are unit vectors. So you will have like 3 constraints for each spin. It has to be a unit vector, but they also need to enforce the angle that they form with each other, which are another 3 constraints. However, if you write them in terms of these R matrices and the basis, then you somehow split this. So the angle they form is just encoded here. So you don't need to worry about enforcing that. And then for these R matrices, you can just, I mean, our SO3 matrices, you can use the quaternion representation. And the only thing that you need to ensure is that these different Qs, the square of them add up to 1. So then we just have this R, we plug it here for this, with these 2 different constants, and that's all we need. And we just solve the model. So doing that, this is what we found, and we managed to find, for instance, the charge 1 Skyrmion. So you see that they look exactly the same as in the previous case for these nuclei. And also remember that I mentioned before, when you have these Hophians, you have like a unit vector. So you can also see like the charge of those Hophians looking at 2 pre-images of this unit vector and see how they link. I mean, at the end here, we have 3 spins. So we can take 1 spin, for instance, the third spin, and do the same. So here we are plotting the red, because in the forum we plot, you will also see that. So the red curve is just the 0, 0, -1. And so the pre-image of the 0, 0, -1 point, and the blue is just, the pre-image of this value for the field here. So this can give you like an alternative vision of these Skyrmions in terms of these position curves as people do for the Hophians. Because remember that this is a general model that when this kappa was going to 1, so basically when all your spins just coincide, then you are in a different model. You are in this Skyrmion model hosting Hophians. And here, as I mentioned, so we are taking the coupling constant. So K1 is equal -1. So that means that the least shift point is at K2 equal 0.25. So we just moved around that point. And indeed, you can see that. So the yellow is the one which is closest to this least shift transition. And indeed is the one giving yellow the larger soliton. Here we could even see that even our lattice perhaps was not big enough because we have some border effect here, right? Because the lattice is here and these are the diagonals. And then we also compare our calculation with the continuum approximation. So we took also this energy functional in the continuum approximation, minimized that, and we got these dots here. And you can see that, I mean, they coincide quite well. So it was a really, really good approximation that's going to the second order here. But we could also, like in this nuclear physics framework, we have solitons with much more numbers, right? Higher numbers. You can study nuclei up to 12 and even more, of course. So we can also have a look here if we can go to higher topological charges. And indeed, that's what we did. So for instance, here we went up to chart number 7. And indeed, these 3 here are quite similar to the ones that I showed you at the beginning from the Skyrme model. So indeed, I was kind of cheating a little bit because when I was asking that if we could have, like this kind of configuration of frustrating magnets, I was already showing you exactly those configurations. And you can see, so this Q equal 4 in the Skyrme model, it has the cubic symmetry. So here is slightly deformed. Then Q5 is totally different. For Q6, okay, we have one which is like in the Skyrme model, but has higher energy than other configurations, and so on. But I mean, you could expect indeed that, because remember that this quartic term here, the one stabilizing the soliton, is different. So it's not a big deal that you indeed can get different configurations. We can just go crazy and go even to higher topological charge. So far, everything that I show, it was for, like these orthogonal spins. So that's why also they look so much like the Skyrme model. But here we have like for different values of this kappa, right, or this angle. So this is the Skyrme model case, let's say. So you have like the 3 spheres, not squashed. And you see that they look similar to this to the solution from the Skyrme model, like this kind of shell-like. But once we start to increase this kappa, so we are approaching more like this Skyrme model, we are going more closer to Hopfions. So then you see that they start to change and to be also more like even knots, right? Because when we are here, for instance, 0.955, remember, 1 is this Skyrme, we even get some links and some, for instance, like the trefoil knot. And you see how they are changing quite a lot also this configuration, which again are just the isosurfaces of the baryon charge, or sorry, of the topological charge in this case. But you can see that you have like quite a lot of different configurations. And indeed, this is something that also happened in the Skyrme model. So when you increase the number, for the baryon number, people have found that you have more and more configurations. So, and that even can be problematic because then at some point you will think about, okay, you need to quantize your model. And for quantizing, you will also need to take into account all those different configurations. So I think it becomes more complicated. But you can see here, so we were managed to find pretty much similar structures, or or to prove that this is frustrating magnets may be able to host also this kind of 3D Skyrmions, which are more similar to the one that we had in this Skyrme model from nuclear physics. So let me just summarize to conclude. Like, well, we saw that this Skyrmions, right, was first proposed like an effective field theory for QCD, for the strong interactions. So they try to describe different aspects of nuclear physics. Yeah, it was a little bit forgotten, but then in the last decades, people have started to work again on that. They managed to push the model forward, like doing different calculations, trying to prove and to improve, sorry, some of the pathological problems that they have, like this low binding energy and so on. But then we also saw that it's not only these Skyrmions, but coupling them to the rho meson is also important. So it seems that this is something really necessary, or at least can give you a lot of answers if you if you couple this rho meson. So it would improve a lot. Then we also moved from this kind of nuclear physics to condensed matter physics. So we saw how somehow these Skyrmions are, I wouldn't say everywhere, but almost, right? So you have different systems where they can appear, and they are very famous in condensed matter system. Indeed, I think they are much more well known in condensed matter system than in high energy physics. And yeah, so like this magnetic Skyrmions is like an example, because they also have this technological application, like in spintronics and so on. But they also appear in other realms, right? So like these liquid crystals, where we have like these Skyrmion tubes, and even like more like these 3D configurations that can also appear in this non-collinear, in this frustrating magnets. But again, I mean, remember that the key condition is that we need non-collinear magnets, right? So we need the spins which are non-collinear to be able to find perhaps those kind of structures. So I mean, I don't know if I convinced you, but if I would like to summarize all this, I think then I would say Skyrmions, it's not that they are as precise solitons, but I would say that Skyrmions are versatile solitons, because as you see, I mean, they can appear in different realms all around different fields. So thank you very much.